In this period, we will discuss about Kirchhoff's rules. Kirchhoff's rules. We know Ohm's law to find out potential difference across a resistor if you know the resistance value and current. So that can be applied only to solve circuits with one resistance or two resistors and with one or two cells. But if a circuit has several cells and several resistors, then only say the Ohm's law is not sufficient to solve the problem of finding potential differences across various branches and currents in different paths. Therefore, you require some additional equations which can be obtained with the help of two rules stated by Kirchhoff. So, he gave two rules to solve the problem of electrical circuits having several cells and resistors. According to these rules, the first one is known as junction rule. This junction rule can be said as a consequence of law of conservation of charges. That is, charges will not accumulate at the junctions of an electrical circuit. Suppose if current is coming through several paths and meeting at a junction like this. So this is a junction in a closed electrical circuit. So some currents are approaching. So like this, some currents are leaving. So let us call it as, say, I1 this is, I2 this is, I3, and say the current leaving is, say, some I4. Since we are talking about steady currents, the charges cannot store at this junction. Then if the charges accumulate here, the current values will not be steady or constant. Therefore, for steady currents passing through the different parts of a circuit and if they are meeting at a junction, charge should not accumulate there. Then only the currents will be steady in the paths. So therefore, according to this rule, the sum of the currents, algebraic sum of the currents meeting at the junction must be 0. So we will give some positive sign to the currents meeting at the approaching the junction and give negative sign to the current leaving from the junction. Then we can write the equation for the currents like this: minus I4 is equal to 0. Take this minus I4 to the other side. Then we can write like this: I4. So this is how we apply junction rule for finding the relation between the different currents meeting at the junction. The next one is loop rule. So, loop rule is a consequence of law of conservation of energy. In a closed circuit, if the energy is not lost in any form like heat or electromagnetic radiation, then the electrical energy must be within that circuit. So, the sum of the algebraic sum of the potential differences across various branches of a closed network or a closed circuit must be 0. While applying this rule and for writing the equation for the potential differences and EMFs, we must follow certain rules. That is, the currents are represented by arrow marks through the resistors along which if you travel, so you may take that direction as positive, and you can take even the potential difference from the one point to the point in which the current is flowing. So that potential drop, so in some books they take positive and in some books they take it as negative because there is a decrease in potential energy or the potential decreases. So we call that as the voltage drop or potential decreases. Hence we may take negative or positive also can be taken according according to some other textbooks. But I am taking it as negative because I consider it as voltage drop. Similarly, the EMF of the cell is taken positive if the current traversed through the cell is from negative terminal to the positive terminal. And if the the direction in which you travel is from positive to negative, then that EMF, which is opposite to the current direction itself, is taken as negative. Keeping these two important rules in mind, let us take one example of an closed electrical circuit and apply the loop rule. So let us consider a cell, and suppose it has a resistance, say R1, and EMF is E1, and here is another resistor. Let us take another resistor, so call this as R2, and here say we consider a cell such that you take it like this. So we take it like this, and it has a resistance, say some R3, and this is E2, and then here we take one more resistor, so let us call it as R4. So this is a part of a network and it is a closed path. Now, so let us say this is A, B, C, E. Now we give the direction of the current and we represent it by an arrow. So let us suppose this is the current direction it is, and here it is. So we are following a clockwise direction like this. So let us say in this path the current is taken as I1. Here in this path current is say I2. In this path I3, and in this path let us say I4. So these are our assumptions, because why we are not taking the same current means, so there are junctions at which some currents may be coming or may be leaving. Therefore, the currents need not be the same in different paths. So we have taken different values. Now we follow clockwise direction while writing the equations for the potential drops and EMFs. Now I will start from here. See, current is being discharged from this cell E1 of EMF E1. Therefore, the current will be from negative terminal to positive terminal in this cell. Therefore, I will give positive sign. So E1 positive. Then I will go like this. So from higher potential to lower potential I will be. So I think the voltage is decreased. So minus I2 R2. So potential difference I have taken it as negative here. Higher potential, lower potential, there is a drop. So I do negative sign. And I travel like this. Here, see, the current direction is from higher potential to lower potential. Therefore, I will take this as minus E2. So actually current in the cell travels from negative terminal to the positive terminal inside the cell. But we are going in opposite direction, hence minus E2. And again here, the path is from higher to lower. So in this resistor, minus I3 R3. Again here, minus I4 R4. So that is 0. So I will keep EMFs one side and voltage drops to the other side. So I will take the voltage drops to the other side. Then E1 minus E2 is equal to, if I take this other side, I2 R2 plus I3 R3 plus I4 R4. So this is the equation. So in this way we can apply Kirchhoff's loop rule to a closed mesh and can write the equation relating the units and potential differences. Okay, now we apply both the rules to what is known as Wheatstone bridge, and we are going to derive a relation between the resistors in the bridge circuit under balancing condition. So that is called as Wheatstone bridge principle. So let us discuss about Wheatstone bridge. So Wheatstone bridge is an electrical circuit with 4 arms. So the 4 arms can be represented like this. So this is one arm containing some resistance, and this is another arm, and similarly here there is another arm, third one, and this is the fourth one. So there are 4 arms. So let us say the resistance here is say R1. Here let us say if that is R1, we take this as R2, this as R3, and this is R4. Okay. Now it has 4 junctions, A, B, C, D. Now 2 opposite junctions, a pair of opposite junctions are connected by means of a galvanometer. So this is a galvanometer whose resistance is say capital G. Now to the other opposite junctions, a cell or a battery is connected to pass current through a key. So let us suppose here is a key, and is the positive terminal. So this is the battery, say of EMF E. This is the key. So consider current coming from the positive terminal. Say this is I. Here it branches out into 2 parts. That is, let us say through this resistance R1 current is I1, through this current is I2 through R2. So let us assume it like that. So this current I1 again here branches out. So let us assume this is I3 in resistance R3 through the galvanometer. Say the current is say some Ig. Here this I2 and Ig are meeting at this junction, and let us suppose this current becomes I4. Let us represent it like this. Now we will apply loop first junction rule to these junctions, and we will write the relation between the currents, and later we will apply the loop rule. So applying junction rule to junction A. First let us apply here. So very easily you can see I1 plus I2 is equal to I. Let us apply it to B. So here this I1 is equal to I3, and therefore Ig plus I3 must be equal to I1. That equation is understood. And then here at D. So at D, this I2 and Ig are meeting. So Ig plus I2, they combine, and this becomes I4. And finally at C, this I3 and I4 are coming in approaching. So let us take it as positive. So I3 plus I4, and it becomes I and comes out like this. Okay. So that is how we apply junction rule to the 4 junctions. Similarly, applying loop rule to, here there are 2 loops. So this is one loop, this is another loop. So that is ABDA. Now we will follow clockwise direction. Here also clockwise. So when we go in this direction, so I am taking the potential drops negative. So I1 here, if it is traversed in the actual current direction. So I1 R1. So that is minus I1 R1. And again here G is the galvanometer resistance, Ig Rg, potential drops. So therefore minus Ig capital G. So that is capital G is taken as resistance. Then I am coming like this. So I am traversing in the opposite direction. So it is plus I2 R2. Plus I2 R2. So that is equal to 0. So there is no cell included in the closed path of this circuit. So therefore I will take this is plus. So I will take this negative to that side. Then what I can write? So I2 R2 is equal to I1 R1 plus IG into capital G. Similarly, applying loop rule, to the second loop, that is BCDB. So we will start like this. I3 R3. So I am traversing the direction of the current. So minus I3 R3. Now I come like this. So but opposite to the current direction shown. Therefore it is plus I4 R4. Plus I4 R4. Then again, so traveling in the opposite direction like this. So current is coming like this. Plus IGG. IG current. So this is 0. So take the negative values to the other side and keep this positive value. This can, or you keep this here, take that there. Negative signs you can cancel out. Then you can write like this: I3 R3 is equal to I4 R4 plus IG into G. So like this you can write. Now let us give some numbers. Let us call this as equation 1. This is equation 2. And say this is 3. Say this is 4. Now these resistances are such that they are adjustable. So we can say they are nothing but resistance boxes. Consider them like that. So by adjusting the resistance boxes or adjusting resistors, by changing the values in any of the arms of the resistances in the Wheatstone bridge, the potential at B and potential at B are made equal. So if the potentials are equal, there will be no current in this path. So as long as there is potential difference, then only the current will flow. If there is no potential difference, current will not flow. So we make the potential at B and D equal by adjusting the resistances in the arms. So suppose you have done like that, then IG has become 0. Then there will be no current along the galvanometer path. So this is called as balancing condition. So this is called balancing condition. So once the balancing condition is obtained, then what happens to the equation? So from 1 and 2, you observe this. From 1 and 2, IG will be 0. Therefore, I1 is equal to I3. I1 is equal to I3. So I3 is equal to I1. Both are the same. And I2 is equal to I4. I2 is equal to I4. Similarly, see the equations 3 and 4. From 3 and 4. So in 3, this term becomes 0 because IG is 0. So therefore, I1 R2 is equal to I2 R2. And here IG is 0, therefore this term is 0. I3 R3 is equal to I4 R4. Now let us divide 1 by the. So let us call this as 5th equation, 6th equation. So 5 divided by 6. So let us divide equation 5 by 6. So that is I1 R1 by I3 R3 is equal to I2 R2 by I4 R4. But your I1 is equal to I3. I1 is equal to I3. And I2 is equal to I4. So you can write like this. But I1 is equal to I3 and I2 is equal to I4. So here we have shown already. So therefore we can cancel. Then what remains? R1 by R3 is equal to R2 by R4 R, you can write R1, bring this R here, take that R3 there, is equal to R4. So both equations tells us that under balancing condition, ratio of the resistances in the opposite arms are equal. So that is R1 by R3 is equal to R2 by R4. R1 by R2 is equal to R3 by R4. Both are of same meaning. Therefore, the ratio of the resistance in the opposite arms are equal under balancing condition of the bridge. So this is called Wheatstone bridge principle. So this is the Wheatstone bridge principle. Now, what is the use of this principle means? If you know the 3 of the 4 resistors and you don't know any fourth one, that can be calculated. For example, you know R1, R2, R3, you don't know R4, then you can write like this. So that is R4 from that equation is given by R2 by R1 into R3. So like that, by balancing the bridge, if you know any three of the resistors, the fourth one can be calculated. So that is the application of Kirchhoff's law to Wheatstone bridge. Okay. Now we will apply this Wheatstone bridge principle to arrive at the principle of a meter bridge, and also we will discuss potentiometer in the